Hi friends, welcome back to new session. In the last session, we started speed control of DC motors, and in this speed control of DC motors, I think I told you three methods are there: field and flux control method, armature resistance control method, and third one armature voltage control method. In the last video, I explained a field and flux control method for shunt motor and for series motor. Okay, now let me go for armature resistance control method. So first of all, let me apply this armature resistance control method for shunt motor and for series motor. Then I'll go for armature voltage control method. So let us see armature resistance control method. Yes, armature resistance control method. First of all, let me take a D shunt motor. So since this method name is armature resistance control method, I'm adding some extra resistance value. I'm adding some extra resistance value in series with armature so that I can control the speed of DC motor. So you know N proposed EB pi is relation. EB means V. In a DC shunt motor, generally V means what is the formula? EB plus IARA. If there is no armature resistance, if there is no extra resistance in series with the armature. Suppose if I add extra resistance value in series with armature, in addition to this RA, you'll get REX value also here. Okay, REX. Okay. Yes. From this, if you want dB value, I can write EB equals to V minus IA into RA plus REX. Okay. So this one only I wrote here. N proposed EB pi proportional to, in place of EB, I wrote V minus IA into RA plus REX by pi. Okay, and let us see guys here, what is the voltage appeared across this shunt field winding resistance supply voltage? Nothing but V value. So if you want me to write formula for ISH, nothing but shunt current ISH value. So general is nothing but IL, no? It's nothing but IL value. It will divide as IA and ISH. Okay. So ISH formula, if you want me to write, I can write across this voltage, I can write V by RSH. Okay, this is the formula for ISH. As long as supply voltage is constant, so I can say ISH remains constant here, because see, just like I the previous method, in a field or flux control method, I connect some variable resistance in series the field. So that's why there I took a flux as the variable. Now here, if you see, I am not having any extra resistance value in series with a field winding, or I can say I don't have any variable rheostat in field circuit. So simply IS equals to V by RSH. As long as supply voltage V is constant, ISH remains constant. I can say flux remains constant. So guys, please try to understand. So I'm since for DC shunt motor, since I don't have any variable resistance in series with the field circuit, I can take flux equals to constant here. Flux equals to constant. Okay. Right. So now let us see here. In this method, what I'm doing here, so let me take directly flux as constant. There is no need to consider this flux, because I don't have any variable relations here, and ISH equals to V by RSH. As long as supply voltage V is constant, I can say ISH remains constant. Okay. So now my question is, so this implies N proportional to, in place of VB, I can write here V minus IA into RA plus REX. Now tell me guys, suppose if we add RX value, if I add RX value in series with armature, so this IA into RA plus RX will be increasing, this term will be reducing, N will be reducing, right? So as REX is added, I can write IA into RA plus REX is increasing. Okay, whenever this negative term is increasing, what will happen? The speed will be reducing. So that means, tell me guys, in armature resistance control method, we are having below rate speeds or above rate speeds? We are having below rate speeds here. Below rated speeds we are getting in armature resistance control method. Okay. And one more thing I need to ask here. Suppose whenever RX added, you are saying that N is reducing. Okay, because of this concept. Okay. So IA into RA plus RX is increasing, N is reducing, that is okay. As N is reducing, what will happen to back EMF? It will reduce, no? Because you know formula, EB proportional to, I can say N into pi. or x n proportion EB by pi, n proportion EB by pi. From that only I wrote EB proportion to n pi. So I took flux as constant in this armature resistance control method. Okay, so whenever n is reducing, what will happen to back EMF also will be reducing. So simply back EMF will be reducing here. Okay, back EMF will be reducing. So here this main problem in this question is, so just you are justifying your IA variation. This is very important, very important here. Let us see. Generally most of the people will not agree that, here I am just going to say one point. So definitely people will be having some you will be having some confusion with this statement which I'm just going to say. So guys, I'm just adding some RX extra resistance value in series with armature, since I'm adding extra resistance value in series armature, so definitely armature current will be reducing, that everybody knows that. But in this method, I am taking this IA value approximately, I'll take IA value approximately constant here. That reason I'm just going to say, let's just listen here. IA value approximately, I'm just taking constant here. Okay. Here, so many people will be having confusion. So how can you say that like this? Because I'm adding some RX value in series with armature. So definitely armature current will reduce, no? Then why you are saying IA value approximately constant? So I'm saying word approximately, not exactly, it's approximately only. Why approximately is constant? I'm further only, I'm just taking this relation. So let us see if red color is not visible. Let me write once again with yellow color. IA equals to, formula guys. From this relation, IA equals, what is the formula I can write? V minus EB by okay, RA plus REX is a relation. Everybody knows that. Now here my question, guys, try to understand clearly. I'm just going to justify why IA should be taken as approximately constant. Okay, so just listen carefully. So I told you as RX is added, N is first of all, whenever RX is added, whenever this REX is added, it is increasing. So what will happen to this denominator will be increasing, no? So what will happen? IA value generally it will be reducing. Okay, up to this only we will consider, but please try to go ahead. Okay, so if IA in whenever RX added, so I told you from this relation, IA into RA plus RX is increasing, N value is reducing. Okay, whenever N is reducing, I told you back EMF is reducing here. That's very important. Okay, so whenever back EMF is reducing, what will happen to this numerator, guys? Try to understand what will happen to this numerator. It will increase, right? It will increase. So this I value, what will happen once again? It will increase. So initially, because of adding RX value, your IA is reducing. Now, because of the reason that EB is reducing, IA is increasing. So I'm not saying that how much it is reduced, the same amount of increasing here. Okay, I'm just saying approximately. I can take approximately IA value. I can take approximately IA value can be taken as constant here. Okay. So please, guys, try to understand. If you are having any questions regarding armature resistance control method, please try to take IA value approximately constant. Then only you can answer. Then only you'll get correct answer. Okay, IA is approximately taken as constant here. Now tell me, guys, in this method, I'm saying that IA, yes, because of this constant, I can take IA value constant. And what about flux? Flux already I took flux as constant. So IA comma flux are taken as the constant here. Constant. Guys, relation T proportional to pi into IA. Whenever IA is constant, flux is constant. What about torque also? Torque remains constant. Okay. Torque remains constant. Okay. And so please try to see here. What about mechanical power? Mechanical power, I'm asking. What is the electrical equivalent of gross mechanical power developed by DC motor EB into IA? And I took IA value approximately constant in this armature resistance control method. Whenever IA is constant, so tell me, as RX is added, N is reducing here, EB is reducing. Whenever EB is reducing, so what will happen to mechanical power will be reducing. So please, guys, try to understand. Therefore, I can write one point here. As Rex is added. As Rex is is added, what happened to your n value? Please try to see. N value is reducing, and back EMF is reducing. And what will happen to your mechanical power? Pmech is proportional to EB. No, Pmech is reducing. So I'm asking one question here. What is relation between n and p? So n is reducing, p is reducing. No, n proportional to p I can write here. N proportional to p I can write. Okay. So please try to understand it. It will be useful for us. N proportional p is very important for us. And please guys try to see here. As whatever I just told, I mean here, just only that only I'm just writing here. As Rx added, I told you n is reducing here, EB is reducing here, P is reducing here. So relation between N and P is a direct relation. Okay. And now tell me. So in armature resistance control method, first of all, let me have some conclusions. So please tell me, we are getting above rated speeds or below rated speeds? We are getting below rated speeds. This is first point. In armature resistance control method, that too for shunt motor, I am getting below rated speed. First point is very important here. Below rated speeds you are getting here. Okay. And in this method, so motor behaves as constant torque. See, torque is constant. No, torque is constant. Constant torque. And what about power? Power is it's a variable, right? It's a variable. So in motor behaves as constant torque, variable power drive. It's very important relation. Please, motor behaves as constant torque, variable power drive. So let me take on y-axis torque, power. Axis, let me take speed here. Here I took here speed as the n rated value, rated speed, and right hand side of the n rated, I am just taking n greater than n rated. Left hand side I have taken less than n rated. I am saying in armature resistance control method we are getting below rated speeds here, below rated speeds. So below rated speeds somewhere here, yeah, somewhere here. So guys, please try to see your motor behaves as what is it? Constant torque. That means I mean with respect to variation of speed, your torque remains constant. So I took a torque constant like this. And what is the relation between speed and power? As n is increasing, your power is increasing. Yes, p is increasing like this. Okay, guys. So your motor behaves as constant torque, variable power drive. Okay, please try to recollect us these 2 points in case of field or flux control method. Okay, in field or flux control method, if you observe, motor behaves as constant power, variable torque drive. And if you see here, if you see graph, so we are getting above rated speeds. So we'll be here for field or flux control method. So machine motor acts as constant power, means power will be like this. Okay, and variable torque will be like this. Okay. So try to recollect that. Okay, try to recollect field or flux control method. Just try to study by comparing. So if you compare and study, it will be there in your mind forever. Okay. So this is armature resistance control method where you are getting below rated speeds and where motor behaves as constant torque, variable power drive. And regarding that method, this is a graph. Okay, this is a graph. Let us see, guys. Here n proportional to EB pi, I told you, where flux is constant here. N2 by N1 means EB2 by EB1. You know, EB2 means what is the formula? EB2 means what? Suffix 2 means it is by after adding this Rex. So here, if you want me to write the EB formula, V minus IA into RA plus Rex. After adding Rex, okay. So please, guys, try to see here. So EB2 means V minus IA2 into RA plus Rex. After adding Rex, that gives you EB2. Next, EB1, V minus IA1 RA without adding Rex. And here already I told you one thing. IA1 equals to IA2 equals to IA. This I already explained here. Please try to see. This is very, very important point. So in armature resistance control method, you can take IA value approximately constant. This is very, 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 very important point. Okay. Now let us see. I mean, let me proceed for armature resistance control method only once again. See, guys, when with respect to your armature resistance, whatever armature winding will be have some resistance RA. With respect to that RA, this extra resistance will be somewhat more. So obviously, RA is less than REX. If RA is less than REX, so that means RA can be negligible, no? So in this expression, I can write once again like this: N2 by N1 equals to V. Okay, V minus. So I told you IA2, IA1 means IA only once again. IA into. let me neglect this RA, okay, and RA plus RX is there. Then simply write REX only by V. I told you RA is neglected, so IA1 RA will be negligible, okay. So V minus IA Rex by V. V by V means 1 minus IA Rex by V. Okay. So percentage speed regulation means formula N1 minus N2 by N1 into 100. So here once again N1 by N1 means 1 minus N2 by N1, N2 by N1 into 100. 1 minus N2 by, see, try to understand, N2 by N1 value means this one only. So 1 minus IA Rex by V into 100. So if you do calculation, percentage speed regulation equals to 1 minus 1, it will cancel, minus into minus plus IA Rex by V into 100. So guys, try to understand, whenever Rex value is increasing, percentage speed regulation will be increasing. That means if we add no Rex value is increasing means you'll be getting speeds will be reducing. So reducing means definitely speed regulation will be increasing. So no, first speed minus second speed by first speed into 100. No, whenever this N2 is reducing, this N1 minus N2 by N1 will be increasing. No, percentage speed regulation will be increasing. So let us see for shunt motor. For shunt motor, I'm saying, suppose by wearing this REX, let me take total armature resistance RA plus REX. That let us set that value REX1. So for REX1, N versus IA graph, those who are having doubt why you are getting N versus IA graph like this means, so further I had given explanation. Characteristics of DC shunt motor, N versus IA curve is there. Please try to go and refer that. You will be having drooping characteristics like this. So this is, if you want to know how you are getting this graph means, please try to refer that topic. So for REX1, this graph will be drooping like this. Suppose if I go for REX2, which is more than REX1, so I told you speed regulation will be increasing, you know. That means, yes, it is curve is, reduced. Once again, graph is reducing only, but that graph will be below REX1. See, if you want, you can have some idea. Let me take at particular this load, at this load, if REX1 is there, this is the speed. Suppose if I increase the ratio, armature ratio, if I increase acceleration's value in series with armature, so everybody knows that, because if after adding RX value, you are going to have below rate speeds here. So if RX value is more, so definitely your speeds will be reducing. No, see, when compared with your first case speed, your RX2, for RX2, your speed is somewhat reducing here. So that's the reason why your graph will be, drooping only. That too, RX2 graph will be somewhat below than RX1. And guys, let us see for series motor. For series motor, I told you once again, if you want me to draw N versus IA graph, so you are going to have some rectangular hyperbola. Once again, those who are having doubt, please try to refer characteristics of DC series motor, that to N versus IA curve. There I told you. Okay, see, let us try to see that topic, how we are getting this graph. Okay. Let us see, guys, suppose only armature resistance RA is there, I don't have any extra resistance, means at that time graph will be like this. Okay, suppose if by wearing this, I told you in armature resistance control method, I'll be adding some extra resistance value in series with armature. So if armature resistance value is total armature circuit resistance is REX1, which is more than, which is more than RA value. So obviously I told you, you'll get some, if I add some resistance value, speeds will be reducing. No, yes, this curve will be somewhat below than RA curve. If you want, you can check at a particular load. So only if RA is there, at that time, what is the speed? This is speed. If you take REX1, which is more than RA, so the speed will be this much. This is reducing. So obviously, in armature resistance control method, speed will be reducing. Suppose if you still increase armature circuit resistance from REX2 is greater than REX1, so once again your curve will be rectangular hyperbola only, but this curve will be somewhat below than REX1. So once again, if you want to see, so for REX1, but at this particular load, speed is this much, which is less than speed corresponding to REX1. Okay, so simple. After in armature resistance control method, you are going to have below rated speed. As the REX is added, so obviously you will be getting low speeds. We will be getting low speeds. Okay, that's the reason. And see guys, I think I explained here armature resistance control method for DC shunt motor. Okay. So I think the same method will be applicable for same explanation will be applicable for DC series motor also. Okay. For same method applicable for DC series motor also. So those who are having doubt, so please try to see this. Okay. Yeah. I think it is so very simple because in DC shunt motor do we have any effect because of this shunt field winding in this shunt motor? No. See, because of this shunt field winding, do you have any effect here? No. Suppose if you remove this shunt field winding, that becomes which circuit? See, try to see. Please try to have some patience. Please try to follow my words, which I'm saying. I explained armature resistance control method for D shunt motor. That's okay. Now what I am saying is, so whatever the explanation I have given, so where if by adding Rex value, your N is reducing, we are getting below rate speeds, and IA can be taken approximately constant, motor acts as a constant torque of variable power drive. So everything is valid for DC series motor also. Very simple. The very simple reason is, you tell me, in D shunt motor, do we have any effect because of this shunt field winding? No. That means if you remove the shunt field winding, what about this remaining portion? This circuit becomes what? Remaining portion becomes what? It's a series motor only, no? It's series motor only. Simply I'm adding a what? I'll be adding some extra what? RAC. In series motor, in addition to armature resistance RA, extra resistance, I can say series field winding resistance RSC only will be there. That means wherever RA is there, I need to add RSC. That's it. Wherever RA is there, so simply I need to add RSE. So remaining everything is the same for DC series motor also. Okay, guys. Please try to understand that point. So I'll write here. Right here. So let me use yellow color so that it is clearly visible. So armature resistance control method, armature resistance control method for DC series motor, is same as that of what? As that of armature resistance control method, for DC shunt motor, So only exception, what is that? Only something, what is that exception here? In place of RA, I need to add simply RA plus RSC. Remaining everything is same only. So I think here also I can say in just like shunt motor, armature resistance control of shunt motor, I told you some controls. What is that? We are having below rate speed, less than rate speed we are getting here. Number one. Number two, motor behaves as what I said. Motor behaves as, one more thing, a lesser rate space, okay, and IA is taken approximately constant. That was very important point. And motor acts as constant torque, comma variable power drive. So these points I told here. See, constant torque, variable power drive, and IA constant below rate space. Same points applicable for DC series motor also. Okay. So same applicable for DC series motor also. Okay, guys. Try to remember that. And so let me discuss one more point here. Suppose if you want to find efficiency of a particular motor, maybe shunt or series motor, while suppose if armature resistance control method is applying for a particular motor, so they'll give some initially they'll give some speed N1, and by adding some armature resistance value, so they'll get N2 value which is less than N1. So because we are getting a below rate speeds, no. So if they give you N1 and N2, if you want to find the efficiency of a particular motor, I can find out that efficiency. So let me extract that efficiency formula. Efficiency formula means mechanical power developed in a motor by input power into 100. Mechanical power means what here? EB into IA. By input power means what I can say? V into IA. So let me cancel IA. So EB by V into 100. EB means, guys, generally generally EB means, I told you, V minus, if you take example, V minus IA into RA plus REX. in case of shunt. In case of series, Eb equals to V minus Ia into Ra plus Rsc plus Rex. So in shunt, I told you, Ra is less than, very negligible than Rex. Similarly, in series, Ra plus Rsc is very less, less than Rex. That means simply I'm writing here V minus Ia Rex, V minus Ia Rex. In case series also V minus, I will write Ia Rex because I'm neglecting Ra plus Rc because those values are very less. Ra is less than 1 ohm, Rsc also less than 1 ohm. When compared with the Rex, these values are very less. So I can write here V minus Ia Rex in case shunt. Series also V minus Ia into Rex, yes, by V into 100. Okay guys, now V by means 1 minus Ia Rx by V into 100. So if you remember, 1 minus Ia Rx by V means N2 by N1 only. Those who are in doubt, they can refer this. See, so I wrote you here N2 by N1 means 1 minus Ia into Rx by V. See, 1 minus Ia and Rx by V means N2 by N1 only into 100. So from previous slide only I copied this one. So in place of 1 minus Ia into Rx by V, I can write N2 by N1 into 100. Okay. So they'll give you initial speed, and after adding the armature resistance value, they'll give you N2 value which is less than N1. Simply they'll ask you to find efficiency. Your answer will be second case speed. After connecting resistance value, after connecting extra resistance value in armature, at that time, what is the speed? By previous speed into 100 gives you efficiency. Okay, right. And here problem is, you see this equation, you can understand, you can see, you see this formula, you can understand. N2 means what? After adding or some extra resistance value in armature circuit, then whatever the speed you are getting, that speed is the N2. Suppose if N2 is very less, so very less, what will happen? The efficiency will be reducing, will be reducing, See, with simple logic here. So tell me when N2 will be reducing, when you'll get a very less very lesser speeds. So after, if your Rex value is more, by adding very large amount of Rex, so your speeds will be very less. That is not desirable. Why? If I add more amount of Rex, so what will happen to armature copper loss will be more, no? Armature copper loss will be more. Efficiency will reduce. Like that also you can say. Or simply by seeing this formula also I can say. Whenever N2 value is very less, tell me when N2 value is very less, when you'll get very low speeds, when whatever the extra resistance value I'm just connecting in series armature, that extra resistance value is, if it is very larger value, then N2 will be very smaller. So at that time, what will happen? Efficiency also will be less, no? Therefore, guys, wide range of speed control is not possible because as speed is reducing a lot, efficiency also reduces. That is because of more copper losses in external resistance. Very simple logic only. If we add more extra resistance value, so definitely you'll get speeds will be very less. I can understand that. But the problem is, suppose if you add more amount of Rx value, so you'll get lesser speeds, that is okay, but because of more extra resistance value, you'll be having more armature copper losses, efficiency will be less, that is not desirable. So guys, wide range of speed control is not possible here. So up to a particular value of speed only you can reduce. You cannot reduce the speed below that particular value. If you reduce the speed below that particular value, what will happen? Efficiency also will reduce because of more armature copper. Like I say here, because more armature copper losses in external resistance value. So I can say instead of using armature, so already this external resistance value is in series armature only, but let me write simply because of more copper losses in external resistance value. That's enough. Okay. So this is armature resistance control method. Let us see one question based on this armature resistance control method. But that question was that was the previous gate question. That question was asked regarding DC series motor. Though questions regarding DC series motor, guys, I told you, procedure is same. Whatever the person explained here, same thing is same valid here. So I told you where you'll get below rate speeds, where you should take IAVL approximately constant, where motor acts as constant torque, variable power drive, all those things you have to keep in mind. And let us see. So a DC, let us solve this question. It's asked in a gate 2000 for 2 mark. Yeah. A 240 volts DC series motor takes 40 amperes when giving its rated output at 1500 RPM. So initially speed has been how much? 1500 RPM he has given. Okay, right. And again supply voltage also how much he has given? 240 volts. And it's a DC series motor. It's a DC series motor. DC series motor. And initially, how much current is taken? IA1, how much it is taken? How much it has taken? Yes, I think it has taken 40 amperes. Now, its resistance. See, sometimes for series motor, generally, series motor means I can have a diagram like this. It's a series motor. Having armature resistance will be inside, and I can write. I can show yes RSC value here plus minus V IL value ISC, okay, and I can say IA value, RSC value. Sometimes in examination they'll give separately RA and separately they'll give RSC. This much RA value, this much RSC, like that they'll give separately. Sometimes simply they'll call it as its resistance is. Its resistance means you should take this 0.3 ohm as it is a sum of RA plus RSC. Sometimes they'll give individually, or sometimes they'll give a sum of RA plus RSC they'll give. It is around 0.3 ohm he has given. Okay, now what is asking? The value of extra resistance which must be added to obtain rated torque at 1000 rpm. So try to see guys, it's a series motor, no, so the value of extra resistance which must be added means where we can add this extra resistance value. Obviously we can add this extra resistance value in series with the armature only. Let me take armature extra resistance value here is nothing but Rex. Okay, so what he's saying, he's asking to find how much extra resistance I have to connect here so that to obtain rated torque at 1000 rpm. So he's saying that I need a second case speed. How much he has given? 1000 rpm. So try to understand. So indirectly it's a armature resistance control method only, but for series motor, where your if you see observe speeds initially 1500 rpm, now see 1000 rpm, that means you are getting below rated speeds or above speeds. You are getting below rated speeds. You are getting a below rated speeds. Okay, and clearly mentioned the value of resistance which must be added to obtain rated torque. Rated torque means it is acting as constant torque. See, I told you already it is acting as constant torque comma variable power drive. Yes. So now what is asking to find? He's asking to find REX. So I told you guys in armature resistance control method, one thing you have to remember. What is that? This very important point. So maybe these are I'm just showing for DC shunt motor. Same applicable for DC series motor also. I told you in armature resistance control method for shunt motor series motor, IA should be taken approximately constant. That is very important hint for this question. Let us see. Yes, you should take IA2, IA1 will be equals to IA, what of that value? 40 amperes, 40 amperes, 40 amperes. Okay guys, 40 amperes. So now please try to proceed and tell me answer. N proportional to EB by pi is the relation, EB by pi is the relation. Okay, so try to understand. Here one thing you can understand clearly. So T proportional to pi into IA relation is no. Since he said I took the IA value constant, he said torque also constant. You can take flux also constant generally. No doubt. I can say that because Rex is added, your current armature current is not constant. That is exactly you are saying that is okay. But I am saying approximately you can take IA value approximately constant because of this because of this expression, because of this explanation. Okay. So now I can take IA value constant and flux constant and torque can be taken as constant here. Okay. So this entire things will be constant here. Now please tell me N proportional EB pi from this relation N2 by N1 is equals to what guys? EB2 by EB1, EB2 by EB1 into, so I think there is no need to take pi once again here because I told you flux is constant in this discussion. Flux is approximately constant. Okay. Flux approximate constant. What is the reason? Since Ia is approximate constant, flux can be taken as approximate constant. Or simply N2 by N1 equals to Eb2 by Eb1. So please do and tell me answer. So please try to check yourself how much you are getting answer. N2 by N1 equals to Eb2 by Eb1. So guys, Eb2 value V minus second case no Ia2 into Ra plus Rse plus in second case, I am adding this Rex value divided by EB1 means V minus first case IA1 into RA plus RSE. Okay. So now tell me. So I think I told you IA2 value how much? IA2 equals IA1 equals IA equals 40 amperes. No, I can take IA2 value is 40 amperes. I can take IA1 as 40 amperes here once again. So please, we will how much he has given in the question? 240 volts. Huh? He has given 240 volts. He has given 240 volts here. 240 volts. So I think RA plus RSC how much he has given, guys? RA plus RSC how much he has given? 0 0.3, 0 0.3 ohm. Okay, 0 0.3 ohm. And here also, it's not visible. Yeah, 0. Let me write neatly here. Excuse me. 0 0.3 ohm. So 0 0.3 ohm. Yes, 0 0.3 ohm here. And it is also RA plus RS value 0 0.3 ohm. We have to find Rx value, this question mark. We have to find this Rx value. And I think you know N2 value, how much he has given? 1000 RPM. And what about N1 value has given? 1500 RPM. So please tell me how much chance you are getting here by substituting all those things. So N2 means 1000 by N1 means 1500 is equal to okay 240 minus IA2 means 40 into RA plus RS means 0 0.3 plus RX you have to find out divided by. So here we once again is 240 minus IA1 means 40 into 0 0.3. So guys, from this expression, if you can do calculation, tell me how much Rex you are getting here. After calculation, you get Rx value 1.9 ohms. You get 1.9 ohms, or option D is correct. Please just do calculation and you'll get Rx value 1.9 ohms. Okay. Right. This is the question regarding armature resistance control method for a DC series motor, which was asked in GATE 2000 for 2 marks. Okay. Now let us see a last method, armature voltage control method. Armature voltage control method. So actually, armature voltage control method. Let us generally traction applications. I can say traction applications where series motors are used. In those traction applications, this armature voltage control method is used. To be frank, in some industries also, this armature voltage control method is used. Okay, so please tell me what is the formula for N? You know, N proportional to EB by pi. EB by N proportional to EB means V minus IA into RA plus RSC. So, actually, in this armature voltage control method, I'll be using these series motors here. V minus IA into RA plus RSC by pi. See guys, what is the method name here? Armature voltage control method. Okay, therefore we are controlling this voltage. So please approximately take the N proportional to V by pi here, V by pi. And one more thing, in series motors, everybody knows that flux proportional to IA. Is it okay for you, yes or no? If you want those who are having confusion, please try to refer basics. There will be a starting class of your in types of DC machines. I told you. Okay, flux proportional to IA. So guys, flux proportional to IA, that means I can write here N proportional to V by IA's relation. Okay. So try to understand here for armature voltage control method. So where generally this method is used for traction applications where series motors are used. Initially, I am connecting two series motors in parallel like this. Try to understand two series motors in parallel like this. Okay, and what is the voltage applied across each motor? Okay, across armature. I applied V value. So if I assume total current is IA, it will divide as IA by 2, IA by 2. This is nothing but RSC. This is nothing but RSC value. Okay. So it will divide the IA by 2, IA by 2. Now what I'm doing in second case, your two series motors are connected in a series like this. See, one series motor and another series motor like this. Okay. And see, voltage means V. Okay. Since they are connected in series, your voltage divided like this: V by 2, V by 2, V by 2, V by 2. Okay. V by 2, V by 2. And the current IA will be coming as it is. So IA will be here also IA, and here also IA one, because series connection, no current will not change. Let us see. So first of all, in suppose if series motors in parallel, you know formula n proportional to V by IA I told, right? V by IA I told. So NP means parallel combination. I'm saying speed. NP proportional to V means what is the voltage applied. I mean, what is the armature voltage across each motor means V only by what is the armature current in each motor means IA by 2. In parallel combination, I can write IA by 2. It becomes 2V by IA. Next, in one more thing, I told you only n proportional V by A only. So please try to see torque proportional. Torque proportional generally, you know, pi into IA. Everybody knows that. And I told you pi proportional IA also. Therefore, that implies torque proportional. Once again, what you have in relation IA square, no? IA square in case of series motor. So these two are very important for this method. So I'm saying here TP in parallel, if series motors in parallel combination, TP proportional to, so I can write here IA square is, you know, IA square. So tell me what is the IA value here? I can take armature current IA by 2 whole square. It becomes IA square by 4, something like this. So try to remember this NP proportional to 2V by IA and TP proportional to IA square by 4, or I guess IA by 2 whole square. Similarly, guys, let me go for a series connection. Series connection, I'm saying series connection. So NSC proportional to what is the armature voltage across each motor? V by 2 by what is the current? Armature current, I can say, because formula V by IA, no. What is armature current here? IA. IA, you'll get V by 2 IA. This for NSC. Similarly, TSC proportional what? You know already TS proportional IA square. Proportional IA square. Now, what is the value of armature current here? Once again, IA only. Yes, sir, IA only, no? So I can write simply IA square only. IA square only. So now I got NSC proportion V by 2 IA, TSC proportion IA square also I got. Now let us, find out TSC by TP first. TSC by TP. TSC means IA square by TP means IA by IA square by 4. It becomes 4. TS equals to 4 times of TP is the value. Just try to remember. Very important. Next, NP by NSC. NP by NSC means NP means 2V by A, 2V by A by NSC means V by 2IA, V by 2IA, V by 2IA. Okay, V by 2IA. So what is the value you are getting? Once again, 4 you are getting. That means NP is equals to you are getting 4 times of NSC you are getting. Okay. So this is what you have to remember. So maximum students are confusing with armature armature voltage control method with the series and a parallel connection of field winding in flux or field control method. Let me show you. See, generally people are confusing here in a series and parallel connection of field winding. So I got NP by NSC value 2, TSC by TP I got 2. But in armature voltage control method, I'm getting NP by NSC value 4. TSC by TP I got 4. So there is a lot of difference between these two methods. Series and parallel connection of field winding means I'm having only one series motor, and that particular field winding I just made two sections. Initially I connected those two sections in the series, then I connected in parallel. But it's not like that. In case of armature voltage control method, I'm having two series motors. Those two series motors are connected in parallel initially, then they connected in a series like this. So there is a lot of difference. Don't confuse. In this armature voltage control method, TSC by TP means 4, NP by NSC means 4. In series and parallel connection of field winding, TSC by TP means 2, NP by NSC means 2. So don't confuse armature voltage control with series and parallel connection of field winding, which comes under category of field or flux control method. Okay. So this is about speed control of DC motors. Okay. Next, in the next video, I'll be discussing electric braking in a DC motors. Okay, right. Thank you, guys.